Hello, I'm Professor Brian Schmidt, the Vice Chancellor and President of the Australian National University, and here I am sitting in our science classroom, and today is my Masterclass for you to understand the universe.
Professor Brian Schmidt, you have been awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae.
By observing supernovae that exploded billions of years in the past, we can unveil the future of cosmic expansion and understand the universe we live in. The universe is accelerating in its expansion and will exist forever, but will slowly fade away. Now, to understand the universe, we need to have a way of measuring things that make sense. And for that, we use the speed of light. The speed of light's very fast, 300,000 kilometers per second. And to put that into perspective, it means that light could go around the Earth 7 and a bit times in a single second. And as fast as that is, the astronomical distances are so large that even to get to the moon takes light about 1.5 seconds. But if we're going to go on to the sun itself is 5 light seconds across, so much bigger than the Earth-Moon system, but it takes some 8 minutes for light to get from the sun to the Earth. Our solar system extends about 10 light hours out beyond Neptune. That is, light takes 10 hours to get out to Neptune from the sun. And then if we go to even the nearest star, the Alpha Centauri system, one of the 2 pointer stars to the Southern Cross, well, that system is 4.3 light years in distance, 4.3 years for light to get there. That's just the tip of the iceberg. The sky is full of stars, and those stars are one of many spread across the Milky Way. The Milky Way is huge. It's about 100,000 light years across, has roughly 100 billion stars, mostly smaller than our sun, but some larger. And our galaxy is just one. If we go through and take the deepest picture we can using the Hubble Space Telescope, then we see in that tiny little patch galaxies upon galaxies upon galaxies, tens of thousands of them, in this tiny little piece of sky, each one containing 100 billion stars like our sun. We're looking back in time because light takes time to reach us. We're looking back roughly 10 to 12 billion years into the past. And before that, not with a telescope like the Hubble Space Telescope, but rather a telescope that's very sensitive to microwaves, we see a glow across the sky. That we call the cosmic microwave background. We're looking 13.8 billion years in the past when we see this glow, which is an afterglow of the Big Bang. The Big Bang started everything for some reason 13.8 billion years ago, but we don't really know why. Now, I became fascinated about the sky, like I think many children do, and I grew up in the state of Montana in the United States. I had to decide what I wanted to do in life, and I never really thought astronomy was an option. Clearly, astronomy was done by the smartest people on the planet. I wasn't one of the smartest people on the planet, but I didn't know what else to do. And so I went off to university to study astronomy, knowing I'd learn things, for example, physics and math and computing and engineering. And one of the first things I learned at the University of Arizona, that really the beginnings of cosmology, that is the study of the universe, actually happened by someone by the name of Vesto Melvin Slipher. And he did that up in northern Arizona using the telescopes up there. And what he did is he spread the light out of galaxies. And he spread them out in the colors of the rainbow, and he saw they looked an awful lot like stars. But there was a difference. Each of the galaxies that he looked at, the light was stretched redward compared to stars. And he knew what that might mean. He knew that there was a way to stretch light, which is through the Doppler shift. Any object that emits waves, when an object's coming towards you, the waves get scrunched. And when the object's moving away from you, the waves get stretched. Now for sound, when an ambulance comes towards you, the pitch raises. That's because its sound waves get scrunched. Or the pitch goes down as it goes away from you. For light, when you scrunch white light waves, they become bluer. Or when you stretch light waves, they become redder. And so the fact that all of these galaxies' light were stretched redward indicated that all of the galaxies seemed to be moving away from us. And that was a huge mystery. Why would we be a very unpopular part of the universe? It didn't seem to make sense in 1917. But we were able to make progress by going out and making more measurements. And the measurements we needed to do was to measure the distances to those galaxies. Now, the further away an object is, the fainter it appears. That's what we call the inverse square law, because it goes as the square of the distance. So imagine you have a candle and you make it progressively further and further away. It'll appear fainter and fainter. You measure how bright the object is, compare it to a nearby object, and the more distant one will be fainter. That is exactly what Edwin Hubble did in 1929. Now, he didn't have candles in space, but he did have the brightest star in a galaxy. And so he looked at how bright they appeared, and what he discovered that the faster the galaxy appeared to be moving away from us, the fainter its stars. That being, the faster away, the further away. And from that data, which he published in 1929, he concluded the universe must be expanding. Now, why did he say that? I want you to think about a universe that you can, a cartoon universe full of galaxies, that you expand. And when you overlay the before and the after of the expansion, what do you see? You see that nearby objects, when you've blown the universe, when you've magnified it up, have moved just a little bit from the center, which is where we are if you think about in this thought experience. Objects further away, they've moved more. So if we were observing them, the nearby ones will have moved a little bit, and the distant ones will have moved a lot. Exactly what Hubble saw. The further, the faster the motion. And it doesn't matter where in the world you are, everyone sees the same thing. That at almost the same time as these observations were happening in the United States, none other than Albert Einstein was thinking about gravity. In 1907, Einstein had what he described as his happiest thought. When he saw someone, this is maybe an apocryphal story, fall off the roof of a building. And instead of going and getting an ambulance, he thought, I think as that person falls, they must quit feeling gravity. That is, the gravity and the acceleration due to gravity and the acceleration due to moving faster, or inertial acceleration, as we say, were equivalent. And he thought, I think that must always be true. I think they must be interchangeable. It meant for Einstein's equations of gravity, known as his theory of general relativity, that space would be curved by objects and their mass. Now, this idea in 1915 was revolutionary. But should people believe it? Einstein came up with something from thought alone. But in 1919, Arthur Eddington led an expedition to test Einstein's theory of relativity and see if light was bent by the sun. And they could do this by looking at an eclipse at stars behind the sun before and after the eclipse had the sun and the moon in the way. So when they did that experiment, it turned out that the stars were moved by the curvature of space caused by the sun, exactly as Einstein theory predicted. So Einstein's theory of gravity was interesting because it predicted curved space, and it allowed us to go through and think about the universe and how gravity acts on the universe. It turns out Newton's laws didn't work when you tried to think about the universe as a whole. The only answer they gave that made any sense is if there was never anything in the universe, which wasn't very satisfactory because clearly we exist. So Einstein started putting his mind to this, as did other astronomers and physicists of the day. But they quickly realized that the solutions to his equations were dynamic. That is, the universe should be in motion. And so serious was this to Einstein. Einstein actually created a fudge factor. He called the cosmological constant. It's energy that was part of space itself. And it turns out, in his equations, this energy makes gravity push rather than pull. And so he thought, balance out the universe to be steady. Well, it turns out it doesn't work. If a butterfly flaps its wing on the other side of the universe, the whole universe is put into motion. It's unstable. So he later described this as him acting like a donkey for being so persistent and stuck on this. But of course, it was exactly what Hubble saw and demonstrated in 1929. So the view of the universe we have is when we look to distant objects, their light is traveling through space. And Einstein's equation says space is actually expanding or being created. So it's not so much that objects are moving away from us, it's that light is being stretched by the creation of space. So as the light travels through space, the light gets stretched by the expansion of space. So as we look further and further away, we're seeing more and more into the past, and light is getting stretched more and more as it travels to us. But it is a beautiful theory that we use to this day to understand our universe. And I want you to just think a little bit about what this means. Imagine a universe that's expanding. Now let's run it in reverse. What happens? If I think about the past, things will be closer and closer and closer and closer, and there will be a time in the past when everything in the universe is on top of everything else, the Big Bang. If the universe is expanding, the notion of the Big Bang is almost guaranteed to be something about the universe's past. But it seems crazy to have a universe that has a beginning. How could that happen? And we still do not really understand the answer to that question. One of the things that Hubble realized is that when he measured the expansion rate of the universe, it was really about measuring how fast two objects were moving apart. And so you could go through and extrapolate back in the past, and you could find out when those objects were on top of each other by simply essentially measuring how fast the universe is expanding now and running the universe back in time. So measuring how fast the universe is expanding now tells you how old the universe was. This was the coolest thing I could think of to work on. And so when I went off to work on my PhD after the University of Arizona, that is the topic I chose to study, to measure the expansion rate of the universe. The fact that people had been trying to do it for decades upon decades and still disagreed did not deter me. It seemed like a great thing to do. And so in 1993, I proudly found my result. And my result was that the universe was roughly expanding at a rate such that it was 14 billion years old. Very proud of that, and it turns out to be about the correct answer, although it did take the community several more years to agree. Not so much that I was right, but collectively agree on the answer. Now, I want you to think about what I've just said. I've extrapolated the universe back in time. That's great. But if the universe is full of gravity, gravity actually pulls on the universe and slows the universe down over time. So that extrapolation isn't quite right. The universe will actually be slowing down over time. And that means that the universe won't be quite as old as I otherwise thought, just assuming it's doing the same thing back in time. So when I decided to move to Australia in 1994, that was my pitch. My pitch was to figure out what the universe's past was. This is really interesting because if you think about what the universe was doing in the past, then I can extrapolate to the future. And Einstein's theory of general relativity helps me do exactly that. If the universe doesn't have much gravity in it, the universe keeps expanding forever and ever. It just keeps going without slowing down. However, if the universe has enough gravity, then the universe will slow down enough that sometime in the future, probably billions upon billions of years, the universe will stop expanding and then gravity will bring it back to Earth, if you think about it like throwing a ball up in the air, such that in the future, there will not just be a Big Bang, there will be a Ganab Gib, the Big Bang in reverse. And so if you can understand the past, you can understand the universe's future. Because the slowing down of the universe affects how old we think the universe is from the Hubble constant, that is how fast it's expanding right now. It tells us the ultimate fate of the universe, and whether or not it's going to live forever or die. And finally, because space is curved, it turns out it tells us the shape and weight of the universe. So Einstein's theory tells us that a heavy universe is actually curved onto itself like a sphere. That universe is finite in time. It goes, reaches a maximum size and falls, but it also bends onto itself in 4 dimensions, hard to get your head around, such that if you go out that way, eventually, if you had enough time, you could come back to where you start. Crazy, but true. A light universe, one that doesn't have much gravity in it or is empty, actually is shaped like a saddle. It bends hyperbolically away from itself. And then there's the just right universe, the universe that has just the right amount of stuff to sort of come to rest at infinity. That universe is flat. Its triangles add up to 180 degrees, whereas the other universe's triangles have more or less than 180 degrees, depending on if it's open, that is the hyperbolic light universe, or closed, the heavy spherical universe. So, my pitch in 1994 was to go through and make the measurements of the universe's past back in time. So if I could measure how fast the universe is expanding now, and then do that same experiment for very, very distant objects, I'd be looking back billions of years in the past, and therefore I could tell whether or not the universe was expanding, for example, faster in the past and slowed down a little bit or a lot. If it only slowed down a little bit, then I know the universe exists forever. But there's this critical trajectory where the universe is slowing down fast enough that I know it eventually is going to end. On one side of that critical trajectory, the universe is finite. On the other side, the universe is infinite. It was a really challenging thing to do in 1995 because these new digital cameras were big. They had, for example, we had cameras that had 8 megapixels. Doesn't sound that big now, but that was a huge amount of data when we had computers and hard drives that were a fraction of our current power. So one of my jobs was to write software that could go through and find a needle in a haystack. So after 3 hard, long years, we were able to go through and see what the universe was doing. I can still remember back to 1997 when my colleague Adam Rees, who was leading the investigation at this point, and he called me up and said, "Look at this." And the data looked like not what I was expecting. Rather than the objects in the past indicating the expansion rate was faster and had slowed down, they were the opposite part of the diagram. They were at a place where the universe was expanding slower in the past and had sped up. I have to admit, I thought we had done something horribly wrong. But we checked and we checked and we checked. And for everything that we could do, we could not find any mistake we had made. And so in 1998, we announced to the world that we had discovered evidence that the universe was speeding up. It was accelerating in its expansion. Now, that was a big claim in 1998, and it's taken many, many years. But every way we look at the universe, we see that acceleration. And it is for that discovery that myself and Adam Rees and Saul Perlmutter from the other team, because they found the exact same thing, received the Nobel Prize in 2011. But it's worthwhile noting that there was a large team of astronomers behind that discovery on both sides. So, what is pushing on the universe? Why would the universe be speeding up? Well, like most things in astronomy, we go back to Einstein, because Einstein's big mistake, the idea of having energy pushing on itself and making gravity work in reverse, it's exactly what we need to solve this problem. We need energy as part of space, the cosmological constant, or something like it, to be counteracting gravity and making the universe speed up over time. So it turns out Einstein's biggest mistake appears to be my biggest discovery. But you need to have about 70% of the universe be this energy, which we call dark energy, sort of a generic term for anything that causes gravity to push rather than pull. And so you need a balance of a universe which is about 70% dark energy and 30% gravity that pulls. Big claim, and so people immediately started testing it. And one of the first people to go out and test it was a group of astronomers in Australia and the UK, led by ANU's Matthew Collis, in something called the 2DF Redshift Survey. And the idea is that when the universe was formed, it was kind of smooth, had little tiny bumps, and gravity magnified those bumps and ended up creating the stars and the galaxies as we see it today. So we can model that in a computer very accurately. When we go out and we map out how the galaxies are distributed around the sky, they form a foam pattern. And that foam pattern looks like what we model in the big computers of gravity taking what we started with just after the Big Bang to the present day. But the foam structure looks a little different depending on how much stuff there is in the universe. And so you can literally weigh the universe using this technique. But there's a catch. You can only measure gravity that pulls. It's completely invisible to the gravity that pushes this experiment. And this experiment, when it was done in 2002, revealed that the universe was heavy, but not heavy enough to make the universe flat. That is, it was 30% of the way of having enough gravity that pulls to make the universe flat. I want you to remember that number compared to the one that we were suggesting from our measuring of the acceleration. We needed a balance of 70% pushing, 30% pulling. So that's part of one of the experiments that helped explain things. But there's a little catch. Since about the 1930s, whenever we go out and we see how much gravity that pulls there is, it's always a lot more than the atoms we can see. So we can count how many atoms there are in galaxies, and we figure out how much gravity there should be. The number is always about a factor of 6 larger, and that is true of this experiment. The amount of gravity we saw, that 30% necessary to make the universe just right, balance between the infinite and the finite, well, that's 6 times more than the gravity we could add up in the atoms. So a mystery. The other experiment that came along in 2003 was done using that afterglow of the Big Bang, the cosmic microwave background. Now, one of the important parts of the cosmic microwave background is that it enables us to probe that missing material, which we think is something that we call dark matter. Material that has gravity, but it's invisible. And invisibility in physics means you don't interact. You can travel right through you, me, the Earth, without effect. And so that dark matter is something that we want to have a look at. So the cosmic microwave background allows us to do it because that image of the sky 13.8 billion years ago is a snapshot of the universe. What we see are lots of little bumps and wiggles in it, and those turn out to be waves, sort of splash marks left after the Big Bang. So it turns out that you can think of the universe as a giant pond that you throw a bunch of rocks into. And what happens with the waves depends on what the pond is made out of. If it's honey, it has a different set of waves than if it's water. The universe is the same thing. So the Big Bang was like throwing gravel into the universe, and you get a bunch of splashes, and then we get a snapshot about 300,000 years after the Big Bang with this cosmic microwave background. And the number of ways, how big and how many, can tell us actually what the universe is made out of. And so that experiment, done in 2003 very accurately, demonstrated how big the waves were and what the universe was made out of. And so it turns out that the theoretical expectation of the universe that in 1998 we predicted being made out of this dark matter at about 30% and 70% mystery matter turns out fit almost exactly the data that we went and observed in the cosmic microwave background. And it measured very precisely that there is about 6.5 times more dark matter than normal atomic matter. And it turns out it also enables us to measure how much dark energy there might be in the universe, because the size of those sound waves are something that we know from physics itself. And how big those sound waves appear depends on the shape of the universe. If the universe is curved onto itself, like it's finite, then that turns out it magnifies the size of those waves. They look bigger. If, on the other hand, it's curved away from itself, that demagnifies. They look smaller. And if it's just right, then they have a size in between. And it turns out this measurement very clearly shows, to with much better than 1%, that the universe's shape is just right. The universe is perfectly poised between being finite and infinite. So this can all be reconciled because the two types of matter, the matter that makes gravity push and the matter that makes gravity pull, both add up to make the universe have its shape. So we know from the cosmic microwave background that everything adds up to 100%. We know 30% of it is the stuff that pulls from the galaxies, from the supernovae. 70% left over is this mystery matter pushing. 95% of the universe is stuff that we don't see here on Earth. 5% is atoms. That's the stuff we are made up and we know the Earth is made up of. But 70% has to be this stuff we're calling dark energy, stuff that makes gravity push. 25% dark matter. This is matter that has gravity that pulls, like atoms, but can travel right through the Earth. Now, you might be thinking, if you have to make up 95% of the universe, maybe it just means you don't know what you're talking about. But we've been able to predict what we should see again and again and again. And like it or not, science is about having a theory that predicts things and then going out and testing it. And this crazy model has been able to predict everything that we've been able to measure at this point. And so I don't tell you it's exactly right, but it's pretty good and a pretty good way at understanding how the universe is working. So what's it mean for the future? Well, if you think about dark matter and dark energy, you have gravity that pulls and gravity pushes. There's a battle for domination of the universe. Dark energy versus dark matter and atoms. The fact that dark energy is 70% and pushing the universe apart, well, I hate to say it, dark energy has already beaten us and the atoms we're made out of. And that's because dark matter and atoms are in space, and as space expands, we don't expand with space, we just stay the same. Space gets bigger and bigger and bigger, and so our density and our gravity diminish. Dark energy, that's part of space itself. Dark energy, as space gets bigger, there's more of it. Its gravity stays the same, its density stays the same, and it continues to dominate more and more and more. So We are in a battle lost. Dark energy is the future of the universe. And as the universe gets bigger and bigger, dark energy can push harder and harder on the universe and make it expand faster and faster. The expansion of the universe will run away, not dissimilar to a COVID epidemic. It's an exponential runaway, such that eventually galaxies that we can see today, the light they emit, will be traveling in a space that's expanding so quickly that the light will literally get stranded on its way to see us and never reach us. So things we see today will disappear. Now, it turns out it's hard to know exactly what's going to happen in the future because we don't know exactly what's in the universe and how everything works. So unless for some unknown reason dark energy suddenly goes away, it appears that the universe will, at an ever-increasing rate, expand faster and faster and fade away. So it's a good time to keep studying the universe because we're losing information every day. Thank you for watching my masterclass.